Good morning students. In this class, we will discuss about preparation and properties of amino compounds as a revision and also discuss some model questions, right, for practice. Now, when it comes to the first method of preparation of amino compounds, Hoffman ammonolysis of alkyl halides. This method is also called as Hoffman ammonolysis of alkyl halides. Alkyl halides reacts with ammonia to give the corresponding primary amines. So, the major question possible on this reaction is it follows which approach? It follows a nucleophilic substitution bimolecular, means rare side attack. Okay, rare side ascent to approach it follows, giving a primary amine. This on further reaction gives secondary amine, on further reaction tertiary, and finally it gives quaternary ammonium salt called as Hoffman ammonolysis of alkyl halides. Next, second method is alkylation of azide. Suppose a sodium azide or potassium azide or any azide. Azide, when treated with alkyl halide, even this also follows. This is a nucleophile. It approaches from the rare side of this alkyl halides. It follows a SN2 approach and gives alkyl azide. It is called as alkyl azide. This alkyl azide on reduction in presence of sodium and alcohol and lithium aluminum hydride as reducing agent gives primary amine. Another example for this alkylation of azide is this one, sodium azide when treated with epoxide had given, see this is a trans attack. A trans compound is formed, which on further reduction, this azide on reduction, catalytic reduction had given the corresponding amine. Right. Now, these two methods comes under alkylation of azides. And third one is Gabriel thalamide synthesis, where nucleophile is thalamide. See, this is especially an important method for the preparation of primary amines because thalamide can only be subjected to monoalkylation. Thalamide can be subjected to only monoalkylation. So, this is thalamide. When treated with a base, it gives potassium thalamide. This itself is the nucleophile. Thalamide itself acts as a nucleophile. Now, this thalamide when treated with alkyl halide, even this also follows SN2 approach. Nucleophilic substitution bimolecular SN2 approach, giving alkylated thalamide, which on further reaction with the hydrazine in presence of alcohol, and on refluxing the mixture, we will get thallyl hydrazide and the corresponding primary amine. As we discussed, as this can be only, there can be only one alkylation possible here. This method is very important and the best method for the preparation of primary amines. When it comes to the other methods of preparation, amines can be prepared from nitro compounds, nitriles, oxymes, C double bond NOH, that functional group is oxime, amide, and even from aldehydes and ketones also. Right. See, what are the list of functional groups? Amines can be prepared by using nitro compounds, nitriles or cyanides, or oxymes or amides and aldehydes and ketones. How? Nitro compounds can be reduced to the corresponding amines either in presence of nickel, palladium or platinum catalytic reduction, or using an acid catalyst and inexpensive, less expensive metals like tin, iron, zinc, stan and compound salts like stannous chloride, etc., SnCl2. So, in presence of any one of these less expensive metals and HCl or an acid, nitro compounds can be readily reduced to amines. This is one of the best method, just similar to that previous one, Gabriel thalamide synthesis. And when it comes to the other functional group, nitrile cyanide functional group on direct reduction, either by using hydrogen in presence of catalysts, that one is adsorption phenomena, or using a strong reducing agent like lithium aluminum hydride also, we can get the primary amine. Similarly, oxymes which we can obtain from aldehydes, oxymes can be generated from aldehydes, you are aware of that. Oxymes when reduced with lithium aluminum hydride or catalytic reduction hydrogen in presence of nickel, palladium or platinum, or reduction using sodium and ethyl alcohol. See, we have to remember that these conditions are for reduction. Okay. In presence of any one of these reduction condition, we can get primary amine. Similarly, this is an amide. Amide when subjected to reduction with lithium aluminum hydride, we can get the corresponding amine. Of course, this is a, here it is a tertiary nitrogen, right, tertiary amine. So, tertiary amine is generated, tertiary one because it is connected to 2 carbon chains there. These are all, see, without any change in the carbon chain, without any change in the carbon chain. Next is reductive amination of aldehydes and ketones. Reductive amination means it is an addition reaction shown by aldehydes and ketones, we discussed in the yesterday's class, right. So, when aldehyde or ketone carbonyl group is added with an ammonia, we can get imine, right. This on further reduction, gives cyclohexyl amine. So, reduction, we can use any reducing agent for this purpose, right. So, these are all the methods of preparation of amines without change in the carbon chain. Now, let us discuss a method in which carbon chain length varies. This is an example for such method where the obtained amine will be 1 carbon less than the parent compound. This method, as 1 carbon is getting lowered, 1 carbon is lost, this method is called as degradation of amides. Hoffman bromamide degradation of amides, where amide or C double bond O NH2 amide reacts with bromine in alkali to give the corresponding primary amine with 1 carbon less. Here the point to be noted is this carbonyl carbon will be lost in the form of carbonate finally, CO3 minus 2 carbonate, and this alkyl group will be directed or redirected to the nitrogen of NH2 group. So, these points we have to remember, and when it comes to the mechanism, this is an amide. What is the purpose of taking base? What is the job of a base? To remove a proton. We have to remember such points. What is the job of a base? To remove proton. Now, this base removes a proton and generates N minus terminal in this way. It is a conjugate base of amide. As it is generating H plus, this is said to be conjugate base of amide. Now, this N minus gets joined with Br plus electrophile in this way. Purposefully, we are replacing 1 hydrogen with a bromine. Now, you are going to understand that purpose. Now, what happens? Again, a base will be employed. You know the job of a base to remove a proton. Another H plus will be removed by this base. Finally, N minus terminal, electron rich terminal is generated here. See, whenever electron rich terminal is there, groups like bromine, iodine, chlorine, etc., whenever electron density is increased, their leaving group ability will be enhanced. So, now bromine acts as a much better leaving group due to the available electron density. This is the purpose behind placing bromine in instead of hydrogen. So, because of more electron density, bromine acts as a good leaving group. Observe this carefully. When it leaves the site at nitrogen, electron deficiency will be generated. To compensate that electron deficiency, R minus, see bond cleavage here, R minus will be migrated to nitrogen. So, it become NR. Now, because of this cleavage and migration at carbon, electron deficiency will be generated, which will be compensated by mesomeric effect of nitrogen's lone pair. So, everything takes place in step by step simultaneously. See, listen, till here we studied nitrogen's electron density is more with the removal of proton by another base. As electron density is enhanced, bromine's leaving group ability increases, bromine Br minus will leave the site, generating an electron deficiency at nitrogen. To compensate this, R minus will be migrated from here to nitrogen. Okay. And at carbon, electron deficiency is generated now, which is compensated by mesomeric effect of nitrogen. Thus, an isocyanate which was generated, Okay. Here, one more point to be noticed is, we are not at all disturbing the other groups present in this alkyl group. If the alkyl group has suppose chiral carbon and it has some R or S configuration, capital R or capital S I am talking about, some configuration it has, let it be capital R configuration. Then even after migration also, its configuration will be R only, means its configuration is said to be retained. That is what another question possible. Suppose this alkyl group has a chiral center whose configuration is capital R. Product they will give R and H2. The product configuration is capital R, capital S, or cannot be predicted, like that they will ask. As we are not at all disturbing the arrangement of the groups inside this alkyl, okay, we are not disturbing the arrangement of groups inside this alkyl group, the configuration will be retained even after the formation of primary amine also. Understood? And one more point is isocyanate is generated, which on further hydrolysis gives N-alkyl carbamic acid. N-alkyl carbamic acid, which further gives on decomposition gives primary amine with the liberation of carbon dioxide. Now, this carbon dioxide in presence of alkali gives carbonate and water. Okay. Now, every point of this mechanism is important and beautiful. Now, let us come to the salient features of this Hofmann bromamide mechanism. It is equally suitable, I am repeating, this mechanism is equally suitable for the preparation of primary, secondary, tertiary and even aromatic amines also. It is equally suitable for primary, secondary, tertiary and aromatic amines. And the next one is amide connected nitrogen should contain 2 hydrogens. See, presence of these 2 hydrogens is compulsory. If one hydrogen is there and another is alkyl group also, it stops at the intermediate, N-bromamide will be stopped, further rearrangement won't take place. Because for this rearrangement, hydrogen is compulsory, that should be removed by hydrogen and all alkyl group should be shifted over there. When we cannot remove hydrogen, when there is no hydrogen, how can we remove? So, even one hydrogen also not enough. 2 hydrogens are compulsory for this. Next thing is, this alkyl group, rearranging alkyl group. See, this alkyl group is getting migrated over there. If any electron releasing groups are there in this alkyl group, they will enhance the rate of migration and thus enhance the rate of Hofmann bromamide degradation. Even in place of this R, if an aromatic ring is there, in case of alkyl group is replaced by some aromatic ring, presence of electron releasing groups on aromatic ring also increases the rate of reaction. See, methoxy is more influencing than methyl, than hydrogen, than chlorine, than nitro. You know that these two are electron releasing groups, so they increases the rate of migration of aromatic ring than the groups which are coming later, right. This is another method of preparation of amines where the similar intermediate isocyanate formation is involved with a similar alkyl group shift with the retention of configuration. See, this method is courteous Smith rearrangement of acyl azides. See, acyl azide, acylated azide to alkyl isocyanate, which are further hydrolyzed to amines. So, what happened? This is acid chloride. When subjected to sodium azide to react with sodium azide, see, acylated azide is formed. So, one should understand this electronic picture. Now, nitrogen is electron denser here, it has its all the 8 octet set of electronic configuration. Here, this point you need to observe. This is a good leaving group. N2 plus is always a good leaving group. In my previous classes, I had specified the best leaving group is N2 plus. The first one in the decreasing leaving group ability, first one I had given as N2 plus. So, whenever this N2 plus is there, our reaction is getting becoming easier. So, it is a leaving group, it leaves the site developing an electron deficiency here. Whenever there is an electron deficiency, the corresponding alkyl group will be shifted here to compensate that. That is what happens. See, again isocyanate is formed. Same points we can repeat. When there is an electron releasing groups in this alkyl group, it increases the rate of migration. If it is an aromatic ring also, that also possible, same points. Now, on hydrolysis gives primary amine. Isocyanate on hydrolysis gives primary amine. Similarly, we have another reaction called a Smith reaction, where carboxylic acid, instead of acid chloride, we can directly use now carboxylic acid when reacts with hydrozoic acid. Same way, in the same intermediates like RCON3. Okay, acylated azide will be formed, which on further rearrangement gives primary amine with the liberation of nitrogen and carbon dioxide. Now, one more reaction is there, that is called as the Lausanne rearrangement. It is N-carbamic acid, it is carbamic acid in presence of a base. Carbamic acid in presence of a base, CH plus is removed. The job of a base is to remove this proton. Proton is removed. Now, what happens? this due to the presence of more electron density on nitrogen, this OH acts as a good leaving group, it leaves the site. Whenever electron deficiency is generated, again alkyl group is shifted, giving, or see alkyl group here electron deficiency is generated, that this is called as nitrene. This intermediate is called as nitrene intermediate. As it is electron deficient now, alkyl group will be shifted, giving a cyanate, which on hydrolysis gives amine. So, in all these previous method and this one and even Lawson rearrangement also, so there is a formation of cyanate, isocyanate, not cyanate, isocyanate. Now, when it comes to the chemical properties of amines, the most important one is basicity, most important one. In gaseous phase, no doubt tertiary amines are more basic than secondary, than primary, than ammonia. So, we need not debate at this point. But when it comes to aqueous solution, basic nature in aqueous solution, we need to concentrate on three factors. One is what is that called as plus I, inductive effect, other one is hydrogen bonding, other one is steric factor. With respect to inductive effect of the surrounding alkyl groups, with respect to hydrogen bonding in aqueous phase, and with respect to steric factor. With respect to, by considering these three factors, it was finally noticed that in aqueous phase, methylated amines are secondary or more basic than primary, than tertiary, than ammonia, whereas ethylated amines are secondary, more basic than tertiary, than primary, than ammonia. Okay. And for NEET, this is what minimum required. Above this not required, they won't go beyond the NCERT. And basicity of, one more point we need to concentrate here is, basicity of alkyl amine is greater than aromatic amine. So, we need to understand that point. See, in case of aromatic amine, suppose this is an aromatic amine. Suppose it is behaving as a base, aniline, let us take aniline. It is behaving as a base, means it is donating its Lewis base, no? Base means Lewis basic character we are talking about. So, it donated its electron pair to this one, giving NH3 plus, it is called as anilinium ion. As you know the concept, whenever the conjugate base is stable, parent is said to be strong in its nature. Whenever the conjugate is more stable, parent is said to be strong in its nature. This to be called as a strong base, its conjugate acid should be more stable. Its conjugate acid should be more stable, right? But there is no resonance phenomena happening in case of anilinium ion. There is no resonance. In case of aniline, there is a resonance, delocalization of pi bonds takes place. So, lone pair is engaged with in conjugation with aromatic ring. Like that, there is a resonance phenomena happening for the stabilization, whereas no such phenomena happens in case of anilinium ion. As product is less stable than the reactant, formation of this product is more endothermic, means less spontaneous. Right, that is why aniline is said to be less basic than the aliphatic amines. Aromatic amines are less basic than aliphatic amines. And even in case of aromatic compounds also, aromatic and amines also, we need to concentrate at one point. If there is a group on the aromatic ring, if the group is electron releasing like ammonia, methoxy, methyl, etc., then anilinium ion will be formed. No, see, this is anilinium ion. If any electron releasing groups are there on this, they release electron density and stabilizes this charged species. When it is stabilized, when anilinium is stabilized, the parent is said to be strong base. In that way, if electron releasing group is there, they increases the basic character of the corresponding aromatic amine. And if the group is electron withdrawing group, still they increase the plus charge on NH3 plus and destabilize the anilinium ion. So, decreases the basic character of aniline. In that way, electron releasing groups increases the basic character, electron withdrawing group decreases the basic character of, for example, aniline if you consider. In this context, we need to discuss about ortho effect, which plays major role in the properties of amines, like especially in the basic character of amines. Ortho effect is presence of a group, it may be electron releasing or withdrawing. Presence of a group at ortho to NH2 decreases the basic strength of amine, irrespective of its nature, irrespective of whether it is electron releasing or electron withdrawing. Means usually electron withdrawing group destabilizes, right? But whatever the group present at this ortho position, it decreases the basic strength of amine. That is the point called as ortho effect. For example, in this context, if you take aniline with suppose take an electron releasing group OCH3 at ortho position, at meta position, and also at para position OCH3. It is minus I plus M, you are aware of, plus M is more pronouncing, so ring activating ortho para, like that you are all aware of those points. Now usually due to electron releasing group anilinium ion, anilinium means it is a conjugate acid of this NH2. Anilinium ion will be stabilized by the presence of electron releasing group, yes or no? But here, so according to that mesomeric influence, para is more influencing than ortho than meta. So POM aniline, para, ortho, meta, aniline, this should be the sequence. But due to ortho effect, due to the presence of a bulky group at ortho position NH2, this basic character will be decreased. So the sequence changes to para is more basic than meta, than ortho, than aniline. Still meta is more because of electron releasing character. Electron releasing group increases the basic strength in the 10 minutes before we discussed, right. So in this way, presence of a group at ortho to NH2 decreases the basic strength of amine, which is called as ortho effect. And electron withdrawing group at ortho effect decreases the basicity much greater, decreases in a much pronounced way than its position at meta and para. Electron withdrawing group usually decreases the basic strength, but this decreasing effect is more if its position is at ortho than at para and meta. And when it comes to the next test for differentiation of amines, Hoffman's mustard oil test, it is reaction of amines with carbon disulfide to give dithiocarbamic acid, which further reacts with the mercuric chloride to give alkyl isothiocyanate. This alkyl isothiocyanate, along with this product, it gives HGS, black mercuric sulfide also. This black coloration, in fact, it is a test for primary amines. This is a primary amine. So if it is a secondary amine, even secondary amine also reacts with CS2 up to dithiocarbamic acid only. Later, that cannot react with this HgCl2 due to the absence of hydrogen. Due to the absence of hydrogen in secondary amine, it won't proceed further. And tertiary amine anyhow has no reaction with carbon disulfide. In this way, if it is a amine reacting with carbon disulfide followed by HgCl2 giving a black precipitation, see, it stands for primary amine. If it is not giving any black coloration, then it stands for secondary. No reaction means it is tertiary. And the next property is carbyl amine reaction, property of amines, carbyl amine reaction, which is very important, right. This isocyanide itself is called as carbyl amine, you are aware of that point, right. See, aniline when reacts with primary amine, when reacts with chloroform in presence of alkali to give alkyl isocyanide, carbyl amine is another name for isocyanide, and KCl plus H2O. This RNH2, it is not a substitution reaction on the ring, have you noticed? Here also, in this reaction also, as a result of these two, dichlorocarbene, I think I specified, CCl2 is the electrophile generated as a combination of chloroform and an alkali. But that electrophile is not attacking on the ring if it is an aromatic ring, suppose, because NH2 itself will interact. See, that is what the point specified here. RNH2, nitrogen's lone pair, attacks the electrophilic intermediate CCl2 and thus forms alkyl isocyanide, or also called as carbyl amine. In fact, it is a test for primary amines. And when it reacts with nitrous acid, reaction of primary amines with nitrous acid is also of more importance. See, this is how they react with nitrous acid. In presence of H plus, OH will be protonated. Nitrous acid is actually unstable. It is to be prepared in situation. In situation means how? It is prepared as a combination of NaNO2 plus HCl. Gives HNO2 plus NaCl in this way. So the reaction that is associated is HNO2 on protonation becomes H2O plus, which is a good leaving group, generates a nitrosyl cation. This, even that nitrosyl cation also generated by reacting this with chloride, which gives nitrosyl chloride, which is chlorine is more electronegative, so Cl minus plus NO plus. So one should be aware of the intermediate that is possible in the reaction. So in this way, primary amines reacts with nitrous acid H1O2 or this can be generated as a combination of NaNO2 and HCl to give benzene diazonium chloride. Even aliphatic compounds, aliphatic amines also will form such diazonium salts, but they are unstable, they decompose readily, whereas aromatic if it is a benzene diazonium chloride, it is stable below 5 degrees Celsius. I am repeating, the similar reaction is also shown by aliphatic amines also, but they give unstable diazonium salts which decompose with the liberation of H2 gas. So, when it comes to Hinsberg test, primary amine reacts with benzene sulfonyl chloride in presence of aqueous alkali to give a clear solution, which on further reaction with HCl leads to precipitation. Okay. Primary amine with benzene sulfonyl chloride and alkali gives a clear solution, which on reaction with HCl, addition of HCl gives precipitation, that is primary. Secondary amine with benzene sulfonyl chloride with aqueous which gives precipitation, and with HCl addition no change. Initially clear and followed by precipitation is primary, initial itself is precipitation, no change on HCl is secondary. And when it comes to tertiary, it is actually water insoluble. With benzene sulfonyl chloride no change, water insoluble only, but when HCl is added, it gives a clear salt solution. That is a test for distinguishing primary from secondary and tertiary. And let us see this question, correct order of decreasing basic character. Already we studied in aqueous solution, of course these questions will be in aqueous solution only. Correct order of decreasing basic character is, so what will be the order? Actually the nitrogen should be less crowded, functional group should be less crowded for the access of a proton. So nitrogen has to donate electron to a proton, then only it is said to be a base. Whichever is less crowded, that is more basic in character with respect to steric hindrance, right. So which is less crowded among all? This is all primary, all are primary, there is no secondary, that is primary, this is primary, primary and primary. Among primary, the one with less hindrance, less crowd will be more basic. So this is less crowded. So 4 should be most basic among all. So where is 4? So this is starting with 4. Okay, 4 is more basic. Next to 4, among this NH2 at second position, NH2 at terminal, among these two, which is less crowded? This is less crowded than this. It is surrounded by bulky group, whereas it is surrounded by CH2, and this is with 2 groups on both sides. So after 4, next most basic is 2. 4 greater than 2 greater than, then 4 greater than 2 greater than, and 3 greater than 1. So 3 greater than 1. Here it is again tertiary. So tertiary carbon, this one is more electron releasing. So our option will be second option. And when it comes to this question, see this is an amine subjected to reduction, it has a ketone group also. Hence what is X? See here, this is the compound given, ketone group 1, 2, 3, and fourth one is NH2, 1, 2, 3, and fourth one is NH2. Now what happens here? It is a base. At the same time, when it is subjected to reduction, the unsaturation gets reduced quickly. It becomes OH, 1, 2, 3, 4, NH2. Now this OH accepts a proton readily from NH2. NH2 is larger size, both have lone pair, both N and O has lone pair, but because of large size that is more basic, no. So it donates a proton giving it becomes OH2 plus, this is NH minus, and on further reaction it acts as a good leaving group. It acts as a good leaving group, thus the obtained compound will be so where is this answer? It is option C. When it comes to this question, correct order of acidity of molecules X, okay, the hydrogens X, Y, Z, see in the given molecule, how to predict their strength means with respect to the stability of their conjugates. Suppose if this COOH had donated one H plus, it becomes COO minus, the conjugate anion. It should be stable for COOH to be more acidic, right? So, this can be stabilized by the nearby NH3 plus, which is a strongly withdrawing group in the proximity. In the close proximity, and withdrawing group is present here. So, I am definitely among carboxylic acid and NH3 plus, carboxylic acid is more acidic. So, X is greater. Then when it comes to Y and Z, when NH3 plus donates a proton, it becomes NH2, which is stabilized by the presence of electron withdrawing group, whereas such stability is not possible for NH3 plus. So, among X, Y, Z, X is greater than Y greater than Z. So, which option it is? Second option. Now, when it comes to the next question, correct order of basicities of the given molecules. Obviously, let us see one by one. More the stability, more is the basic character. Like if you take the first one, CH3, C double bond NH, NH2. Suppose if it is acting as a base, let us say this is structure 1. Let us take resonance phenomena here, delocalization of pi bonds. So, it becomes CH3, CNH with the 2 lone pairs and with a minus charge, double bond NH2 with a plus charge here. This is structure 2. Now, the structure 2, when accepts a proton, it becomes CH3C NH2 double bond NH2 with a positive charge, which is in resonance with the CH3C double bond NH2 with a positive charge single bond NH2. In this way, there is a resonance stability between these two forms, suppose 3 and 4. So, in that way, as this 2 after protonation is getting stabilized by resonance, more stable products, conjugates are being formed. This is said to be a strong base. So, among all, so 1 is said to be a strongest base among all. 1 is said to be strongest base. Where is that option? Option should be either B or D. And when it comes to the rest of the molecules, this is a tertiary one, which is obviously more than primary. So, tertiary is greater than, more basic than primary. So, 3 is greater than 2. 3 is greater than 2. So, second option.